Hi, everybody. I would like to introduce a new topic for university students. We are going today to learn how to find the inverse of a matrix. So, if we want to find the inverse of a matrix, we should know that, first of all, it should be a square matrix. So we can only talk about the inverses of square matrices in general. And but this square matrix has also some conditions, and we are going to talk about this condition, an important condition which we should never forget for finding the inverse. But before that, let's introduce the formula which we are going to use and which is the main basis of the so-called adjoint method. So if we have a matrix A, then A is equal, A inverse, which is the inverse of a matrix, is equal 1 out of determinant of A times adjoint of A. So before I pass to the realization and example of this formula, I would like to give the definition of inverse matrix. So what is the definition? Which matrices we call inverse? If there exists such a matrix X for which A times X equals to identity and X times A equals to identity, then this matrix X is called inverse of matrix A. So we denote it like this. X equals to A inverse. Actually, in this case, A inverse of X also. So you can write as A is equals to X inverse also. So this is the condition, main condition that defines the matrix to be inverse of any other matrix. For this purpose, if we come back to this formula, you can see here that we have here determinant of A and division by determinant of A. This formula gives us an additional information that if we have determinant equals to 0, then it is impossible to find the inverse of a matrix. So in this case, we say that the matrix is not invertible. Not invertible, instead of not invertible, sometimes we use the term singular matrix. So if determinant of matrix is equal to 0, of course, again, we are talking about the square matrices, then its inverse cannot be found, and it's not invertible, and also we call it singular matrix. So we are going to talk about non-singular matrices and invertible matrices. So we said that in order to have the matrix inverse, we have the determinant. We have to have the determinant of A not 0. So I would like to continue on one example. Let's write an example in using this method. So I would like to introduce a matrix, 3 by 3 matrix. You can apply this method to any size of matrices. 2, 1, 3, let's say 0, 1, 4, and 0, 0, 2. This is, you can see it's a triangular matrix, upper triangular matrix. So you can find its determinant easily. We know that in this case, the determinant of such matrix is 2, the product of these diagonal elements. So it's going to be determinant of A equals to 2 times 1 and times 2. So it's going to be 4 here. So actually we have seen the determinant of A is not 0. So it's not a singular matrix. It means that we can find its inverse and we can apply that formula. So in order to find the inverse of this matrix, we have to just set up such a matrix which is called adjoint of 8, or sometimes called adjugate of A. So adjugate of matrix A. How we can find this classical adjoint? If for this purpose we need to have the cofactors. So let's find the cofactors of all elements here. I am sure that you understand, you know already what's the cofactor. So if I denote cofactor by A1, 1, the cofactor of element 2, it's a cofactor of element 2, which stands on the first row and the first column. So A11 is equal minus 1 to power 1 plus 1, which is determinant, and also we should multiply it by determinant. So it's a minor determinant, which is 1, 4, 0, 2. It's equal to 2. A1, 2. This is the second element here. The second A1, 2 is actually this element. So if we want to find, first we need to find the sign here. Minus 1 to power 1 plus 2 times, if we delay it like this, you can see that the row and column we delayed, we get 0, 4, and 0, 2, which makes it 0. You know, we have to multiply like this, which makes it 0. So A1, 3, this is the determinant of this element 3. You know, it's these elements 3. So it's equal to minus 1 to power 1 plus 3. The sum of this, the sum of indices, I add the sum of indices here in the power. So it's going to be times, if we delay it like this, 0, 1, 0, 0. So it's going to be 0 here, determinant also. Again, I choose such a determinant, such a matrix to have some simplicity. A21 equals minus 1 to power 2 plus 1 times determinant. Actually, you can notice that it is the element, 2, 1 is the element this. So we can delay it like this. So we are going to have 2 or 3 and sorry, so 2 actually is not present here. So if we delete this row and column here, so it's going to be 1, 3, and 0, 2. So you can see obviously it's 2, number 2. So A2, 2 is going to be minus 1 to power 4. Again, of this element, let me make it clear what we find. So it is this element. So we can delete like this. Let's see what is remaining. 2, 3, 0, 2, which is 4. Again, we can find other cofactors. A to 3, let me find this place. A to 3 is equal minus 1 to power 5 times determinant. Well, let's mark it to see clearly what we have here. A to 3 is these elements. So if we delay it like this, we are going to have 2, 1, 0, 0, which makes it 0. Another one, again, we continue the third row. We are going to get A31, which is minus 1 to power 4 times 31 is this element. So you can see clearly that it is going to be 1, 3, 1, 4. So this is going to be 4 minus 3, which is going to be 1. A32 is equal. A32 is equal. Again, minus is going to be with minus. So we are going to find here, to write here. Yes, it's 4. So we are going to find here the element for this element. You see, column and row we delayed, so it's going to be 2, 3, 0, 4. So 2, 3, 0, 4. You can see it's 8. And the last one here, A33, is going to be it's going to have the positive sign. So it's going to be, let me make it clear here. Yeah, A33 is this element. Yes, 2, 2, 1, 0, 1. So it's going to be 2 minus 0, which is 2. So we have all cofactors here. The only things that we need to have is to have the determinant, the matrix, which is called classical adjoint. But before that, we are going to make such a cofactor matrix, which we are going to call it a cofactor matrix. Let's denote it by a plus or a cofactor. We can call it a AC here. That's right, a cofactor here. It's not still the matrix that we need. So we are going to write here all cofactors in order. A1C, A21. These are the cofactors that we have just found. 2, 3, A31, A32, and A33. So let's write everything here that we have found already. So A11 is 2, A12 is 0, A13 is 0. So it's going to be like this. 2, 0, 0. So the other elements are the second row. 0 is going to be A21, 2, 4, 0. 2, 4, 0. And we are going to have here the third one. It's going to be 1, 8, 2. So 1, 8, 2. 1, 8, 2. So it's not still what we are looking for. We are going to have the transpose here. So classical adjoint of A, so or adjugate of A is the matrix which is transpose of this cofactor matrix, which is going to be, if we transpose this, let's write our matrix 2, 0, 0, 2, 4, 0, 1, 8, 2. So its conjugate, its adjugate is going to be you know what's transpose is interchange of rows with columns. So it's going to be 2, 0, 0. The rows become columns. The columns becomes the corresponding rows. So 2, 2, 4, 0, and 1, 8, 1, 8, 2. So what is interesting here, I would like to draw your attention to our matrix. You can see our triangular matrix seemingly its adjugate or adjoint classical adjoint matrix is also we call it triangle. So it's if the matrix is this, there is an interesting property. If the matrix is in triangular form, then its classical adjoint is also in triangular form. So we are going to use this one, and actually we know the formula. Yeah, our formula, if you remember, was A inverse is equal to 1 out of determinant of A times adjoint adjoint matrix A, which is sometimes we write with big letters, some small because the letters, it doesn't matter for any case. So 1 out of, we found the determinant. If you remember, its determinant was 4. You see its determinant is 4 here. 1 out of 4 times this matrix 2, 2, 1, 0, 4, 8, 0, 0, 2. So actually you can check that A inverse times A should be identity matrix, or vice versa. A times A inverse should be identity matrix. Well, how we call it, as I said in the beginning, we call the adjoint method. But however, you should be aware that classical adjoint method fails to be effective when you go determinant. For example, if you have the determinant of fifth order or even fourth order or sixth order, then you are going to have problem in calculating determinants. It will take more time. In order to avoid the time, much time, you can use the elementary row operations. I'm going to speak about in our next video. I hope that you enjoyed this explanation and you are going to use it in the exams in your courses. So hopefully it will bring you some clearness of what we do in linear algebra course. Thank you for watching us. Hope to meet you in our next video.